Okay, students, we're going to be covering the X-ray tube, and this is Carlton's chapter, and it's chapter 6, which is the same as Bouchon. We're going to be covering all the components of the X-ray tube along with what each part does. So it's really important that you know this for your national exam. You have some objectives that you need to be able to define, so make sure you define them. And we're going to go into the production of x-rays to start off. Now, like I said, this is all very, very important that you know this information. So watch this video a few times. Read your chapters in Bouchon and Carlton. You will notice within the chapters that the numbers may vary a little bit. Don't let that throw you off. It's okay. I'm open to either or I'll tell you exactly what I want you to know, okay? So with the production of x-rays, you need a source of electrons. Now, those source of electrons come from your filament, right? So it's on your cathode side of the tube. You need a target or a way to suddenly decelerate those electrons. So we use that on the anode. So your source of electrons come from your cathode, which is your negative side of the tube. Then you have your target, which is your anode. It's on the positive side of the tube. And the source is what we use thermionic emissions to boil them off. The target suddenly decelerates them and changes them from an electron to a photon. In order to get the electrons from one side of the tube to the other, we use high voltage, and that creates a potential difference. And we also need a vacuum, so there's nothing impeding the electrons from moving. All right, so looking at our X-ray tube, we have, there's some things on here that aren't labeled, so I'm going to go through it. You have your anode, which is tungsten. Well, the track is tungsten. It's made of molybdenum. The neck and the base, as you can see down here. So we've got tungsten, which is our track, and then we have our molybdenum base. Sometimes there's carbon graphic on the back, and I'll show you what that looks like when we get to it. We have our envelope. They are typically metal envelopes now because we can ground them, which helps with the gases from sticking to the envelope. So if not, it's Pyrex. So it's a glass envelope unless it's a modern day X-ray tube, which will be the Pyrex. Here is your filament circuit coming in. As you can see, this is the negative side. This is the positive side of the tube. We have our filament, and it's usually a dual filament, so we have small and large, and that's where our thoriated tungsten is, where we liberate the electrons and our electron beam going across. Now, typically it travels at the speed of light. In theory, it does, but the distance is so short that it doesn't actually reach the full speed of light. So coming out of the window, so the window is right here. It's not labeled on the tube, but the window is right here, and that's where the X-ray beam exits the tube. And like I said, this is your molybdenum neck and base. So the base here and your neck is molybdenum. Coming around the back, we have the rotating portion. So this rod right here is the rotating portion of the anode. And you have bearings. These bearings are really important. We're going to talk about them and how they're silver plated for natural lubricant for the equipment. And then we have our armatures. So here we've got our stators, and it uses electromagnetic induction. So here is the base right here, and it goes through here and spins these bearings, which spins the anode. And we're going to talk about failure of the anode and the bearings and the stator and the rotor and all that good stuff. All right, so the function of the cathode assembly. So it's the negative side of the tube. It is to produce the thermionic cloud and conduct high voltage, and it focuses the electron stream using that the focusing cup. So we have our high voltage circuit coming in with our filament circuit here. Coming down is our focusing cup and our filament right in here. So the filament, it's a coil of thoriated tungsten, so it's thoriated. It's 0.1 to 0.2 millimeters thick, and it's 1 to 2 millimeters wide and 7 through 15 millimeters long. And it depends on the tube on what is purchased for the filament on exactly what those numbers will be, okay? The filament length and width impact the recorded detail. So the smaller the filament, the better detail you're going to have. So the filament material is tungsten due to its high melting point. The melting point of tungsten is 3,370 degrees Celsius. And we like that really high melting point because it's difficult to vaporize, which means turn to gas. It still does have a little bit of vaporization with each exposure. So it is turning to a gas, which gives you a gassy tube. You can put a mirror around the tube and eventually cause arcing with the high voltage and ruin your tube. So it is a metal that is difficult to vaporize. That's why we like it. So rhenium and molybdenum, now we use those with mammography. They're also good choices because they have high melting points. So rhenium, and we'll talk about rhenium within the focal track also. So its melting point is 3,170 degrees Celsius, and molybdenum is 2,620 degrees Celsius. So we like those metals also. All right, the dual focusing focus arrangement. There's the one thing that I want you guys to know is that there's one ground wire. So a common ground. So the common ground keeps it the wiring simpler. So here's our large focal spot, focal filament, I should say, and our small filament within the focusing cup, which is made of nickel, right? All right. Thermionic emissions. So you have your filament is heated, and what happens is there's a resistance to the flow of electrons, so heat is produced. Tungsten needs to be at about 2,200 degrees Celsius, and it causes electrons to leave the filament wire and form the thermionic cloud. So the high voltage releases the exposure. So it drives electrons towards the anode target. And right where the target is where the photons are produced. Okay, so we heat the filament, it liberates the electrons, they produce a cloud using the focusing cup, and when we apply the high voltage, it drives them across to the anode. So, tube failure. We have several reasons why the tube fails. One of them is tube arcing. So the vaporized tungsten from the cathode and the anode collects. So the anode does vaporize also. So the tungsten within the cathode and the tungsten within the anode will vaporize. So it collects on the inside of the envelope. So not all electrons are driven to the anode or returned to the filament. So what happens is when you liberate those electrons from the filament, not all of them go back into the filament or are driven across to the anode. So a small percentage are vaporized, and we call that a gassy tube, and it puts that mirror appearance to the tube. And what it does over time is it's a metal. So it's going to add filtration to your tube. So if it's covering up your window, it's adding filtration. So you're going to slowly have to take your exposure and go higher and higher and higher with your exposure. So what happens is when you get a new tube, it finally fails, and you get a new tube, you're going to shoot the same exposures that you used before, and you're going to be way overexposing all your patients. And you're like, why am I overexposing my patients? It's because you had this tungsten over your window that was filtering out a lot of your beam. So now you don't have that, so you don't overexpose your patients when you get a new tube. Okay, so what happens is also when the high voltages is applied to the tube and you have this tungsten coating on the inside of your tube, it will arc. And instead of it going and pushing electrons across, it'll shoot over like lightning and break your tube. So your tube is dead once it does that. Once it arcs, it immediately destroys the tubes. So the metal envelopes can be grounded to help reduce this tungsten buildup, which is good. Another way a tube fails is from the filament breakage. So the filament becomes thin with vaporization. So as it's vaporizing, it gets thinner and thinner and thinner. So breakage is when 10% has vaporized. So rough handling of the tube can break a thin filament. So if you guys slam it into detent, when it's a thin filament, that could be the end of your tube. So be careful. When the rotor is activated, filament is heated and thermionic cloud to the size of MA is selected. This causes most of the vaporization of the filament. So what happens is you guys just hit the button halfway down. So the rotor is going. So when the rotor is going, what happens also is the filament is heated and it boils off the electrons. So it's up there boiling, 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 and that will cause vaporization or early death of your tube. So do it in one sweeping motion. When you do an exposure, push the button all the way down. There's safety mechanisms in there to keep you from exposing before all the electrons are boiled off and the rotor is up to speed. So it won't expose until everything is at the speed it's supposed to be. So olden days, it wasn't that way. You had a rotor, wait for the anode to get up to speed before you expose. Now it has safety mechanisms. So as you just hold down the rotor button, you are vaporizing and wearing out your filament. So the filament life is 6 to 9 hours or 10,000 through 20,000 exposures. So make sure when you are making exposure, you push it all the way down in one sweeping motion instead of just letting it sit there vaporizing. All right, so focusing cup, it's composed of nickel. It has a low negative potential, which is applied to it. So it's negative to begin with, and we apply a low negative potential to it, which causes compression of the thermionic cloud. There's bias focusing cups. It maintains a more negative voltage than the filament, and it keeps everything in an electron stream. So keeps all the kids in the playground, as I say. So here you've got your negative focusing cup, you've got your negative electrons, and it pushes them into a stream across to your anode. So as you can see here, without the focusing cup, the kids are running all over the place. If you have a gate, it's going to keep them more in an orderly fashion. So there you go. Okay, so space charge effect. So a negative charge, electrons push against each other and to get where no more can be boiled off. So what that means is it limits the MA. So there's a constant repulsion between the electrons. The electrons, they're both negative, so they're negative, so they don't want to be next to each other. So they're constantly trying to keep a certain distance from each other. Then you have this focusing cup in there too, which is applying also a negative. So you have these two pushing against each other. So what happens is when you hit saturation, it means that there's no more that can be boiled off. So your space charges, you're at the maximum MA that you can be because there's no more room in the playground for anyone else. The bus is full, okay? So saturation current, so as the kVp increases, a greater percentage of electrons driven to the target. Saturation is when all available electrons have been driven to the target. So what happens is your MA needs to be increased to get more electrons. So space charge, it limits your MA. So you can only have a certain MA on for what you've selected. So only so many are going to boil off, okay? And then there's no more room for any more to be boiled off. Saturation is when you have a high kVp and it pushes all of those across. So all available are driven to the target. In order to get more MA, you need to select a higher level. So if you're at 50, you need to go to 100 or whatever. So as kVp increases, greater percentage of electrons are driven to the target. So for that kVp, the max that you can get is here. In order to get more, you need to set more MA. So as you can see here, this is your tube current in MA, and here's your kVp, and you can see where it saturates. There is no more to go across. No more to go across. All right. So grid bias tubes. So precise control of thermionic cloud is the positive of it. It changes charge of the focusing cup from negative to positive. So it allows for regulate, pulse, and synchronize X-ray production. So it's real quick on off. It's also called grid pulse, grid bias, grid controlled, and we use this in pulse fluoroscopy. So anode assembly. This is the positive side of the tube. It has three functions. So it has a target surface, conducts high voltage, and serves as a primary thermal conductor. So the target surface. It's high voltage electrons to target for conversion to photons. So on the target surface itself is where the conversion of electrons to photons happens. It conducts high voltage, so high voltage from the cathode back to the X-ray generator circuit, and serves as a primary thermal conductor, so spins to dissipate heat. It also has molybdenum, which is a great heat conductor, and sometimes we put carbon graphite on the back to help dissipate heat. So here's the anode assembly. So as we can see, here's your envelope coming around. Here's your stator. It's on the outside of the envelope. Inside you have your bearings. So these are your bearings, and your rotor is right here, your cuff or your sleeve, they also call it. This is your anode assembly. It's molybdenum with a molybdenum stem. And then you have your focal track. Now the track goes all the way around, so this is kind of deceiving. And you have your high voltage circuit over here. All right, so the difference between a stationary and a rotating anode. So as you can see, we have a stationary right here, and this outside is copper. You have your tungsten target right here. So this is a focal spot. Spot is just one spot that it's hitting on the anode. When we come over here, we have your anode, which is made of molybdenum. And then you have your focal track. So right here is your focal track, and it's tungsten and rhenium. Now we use the tungsten due to the high melting at 3370 degrees Celsius, and then we add in the rhenium. The rhenium is really good to allow the tungsten to expand and contract without cracking. So that's really important because with the high heat, the really fast high heat, tungsten tends to crack and vaporize. So we add the rhenium, allowing it to expand and contract as needed. All right. So rotating anode, tungsten rhenium alloy. It has a high atomic number of 74 for our tungsten. The melting point, exposures between 1,000 and 2,000 degrees Celsius. It has a high melting point. And for the rhenium, and for the tungsten, exposures between 1,000 and 2,000 degrees Celsius are perfectly fine. So once we go and we reach the melting point of tungsten, and that usually happens if there's some kind of failure of the bearings where the anode is not rotating. So, and that is at 3370. So the tungsten rhenium is heat conducting, which is great. So rhenium provides that elasticity to expand and contract with the heat. So anode layering, so this is what I was talking about. So when we take a look here, we have the tungsten rhenium alloy on our focal tracks, and then we have molybdenum, which is our base of our anode, and then graphite. It's a carbon graphite. So this is what it looks like typically, and it's super light, and it helps with the heat loads. So the graphite backed anodes can double heat loads, and it doesn't increase the wear and tear on the bearings because it's really light. So if we use any other metal, they're pretty heavy and it wears out the bearings really fast. All right, so mammo equipment, we use molybdenum as our target material. It creates the needed lower energy photons that we need. So the atomic number is 42. And it gives us a more uniform low energy photon, which we need for mammography. And the window that we use to exit the envelope is beryllium. So normal X-ray windows absorb too many of the low energy photons. So what we normally use, aluminum, would absorb too many of those low energy photons that they need. Okay, so normal wear, this is called pitting. So you can see how it looks like it's pitted all over. So this is normal wear. This tube's pretty old. When it starts to pit like this, as you can imagine, the photons probably aren't coming off in an exactly straight manner as we would need them. So this is from extended use. All right, so one way to help keep your tubes working for a long period of time is warming them up. So it's a gradual warming of the anode, and it prevents cracking and pitting. And it helps maintain the vacuum within the tube, and it stress relieves the anode. So warm-up procedures, here's just a basic one. What the main thing that I want you guys to do is close the collimator shutters. and then you make exposures usually every 15 minutes, 1 minute to 3 minute apart, depending on what manufacturer it is and if it's what kind of tube it is. So close the shutters. You're going to make an exposure. This one is 70 at 12 mass, and then you're going to wait 15 seconds. You're going to go 80 at 12 mass, wait 15 seconds, 90 at 12 mass, and then your tube is ready to go. Now, it's really important that you warm up your tube regularly, even if you're not using it. It's important because there's these gaskets on the outside, and it needs to move on those gaskets, and it's important that the tube stays warm. It's really hard for if you don't use it for a long period of time, you go in and you use a cold tube to shoot a patient, you're going to wear your tube out a lot faster. So warming it up regularly every hour, 2 hours is a really good idea. Okay, so the target area. It's a portion of the anode that the electron stream contacts. So there's a lot of different names. There's the target, the focus, the focal point, the focal spot, the focal track. Don't be thrown off, okay? This is where we're going to measure where the source of photons are created. So it's off of this focal track. Everything we use is a focal track because the anode spins, so it's a track. It goes all the way around the anode. So it's our source. So it's source to object distance, or our source source to image distance. So it's our SID. So usually when we pull down the tape measures, it starts at 12 inches or whatever. And that is the distance from the bottom of your collimator box to the actual source of where the electrons are. All right, so anode heat loading. So we use a rotating anode, and it's revolutions per minute, which is RPM, and the diameter of the disc also determines the heat loading along with our target material. All right, so line focus principle. It's actual versus effective focal spot. So your actual focal spot is the physical area on the focal track that is impacted by photons. And your effective focal spot is the area on the focal track that is projected out of the tube towards the object. So the effective focal spot is controlled by the actual focal spot and is determined by the filament size. So if you're picking large or small, it's going to make a difference on your effective focal spot. Also, your target angle has a lot to do with your effective focal spot. So 12 degrees is most common, and 7 through 17 is the range. So if we look here and we look at here, this is the anode angle. This is your actual focal spot, and here is your effective focal spot. This is your focal spot right there and right here. So here's your electron stream coming in, so bombarding the electron stream, and then your actual focal spot, and then coming down is your effective focal spot. And it's determined also by your effective focal spot is determined by the angle of your anode along with your filament size. Line focus principle. As the actual focal spot increases, the effective focal spot size increases. So 2 sizes of filaments. So you have a small for detail, but you can't do high exposures with it. So it's got to be like a hand or a toe or, something, an ankle. It can't be anything like an abdomen. You have a large focal spot, which is great for high heat loads. So there's a thing called focal spot bloom. The focal spot increases in size with an increase in MA. So if you have a really large patient, you're using a large focal spot, it actually gets bigger with the increase of MA. It's called focal spot bloom. Okay, so anode Hill effect. This is a concept that you need to understand. So the line focus causes anode Hill effect. So the intensity is more on the cathode end compared to the anode side of the tube. Now the reason is the anode absorbs photons, most or all of the energy. So if we look here, if we look at A and C, these may have enough energy to come out, okay? So it could absorb all or just some of the energy of the photon, okay? compared to looking at D, F. So you can see they're only traveling a short distance, so they're not losing as much energy, okay, in the anode. So short distance for B, D, F, so higher intensity. So if we look here, you've got your anode, you've got your stream coming across here, it's hitting your focal track, and it's coming out. So more of these are being absorbed compared to up here. So down here compared to up here. So we say the cathode side, fat cat, okay? Fat cat eats more. So here, so there's more with the fat cat. So here's 100%. So straight down, you're getting 100% of your intensity. On the anode side, you're losing 25% of your intensity because this is absorbing your X-rays. Compared to this side, you have a higher intensity because it's not absorbing as much. Okay, so we call it fat cat. Fat, it's 20% above the 100, and the anode is absorbing 25%. So 25% fewer photons on the anode end and 20% more photons on the cathode end. So this is called your anode hill effect, and we're going to use that to our advantage. So a 45% swing in intensity from cathode to anode gives the tube a natural head end. So the anode is at the head of the table. Think of a T-spine. So the thin part is up top and the thick part is at the bottom. So the thicker anatomy should be placed on the cathode side of the tube. So if you're shooting a foot, the cathode should be towards the ankle side, okay, not towards the toes. All right, so the stator, it's located outside the envelope. So there's a bank of electromagnets. When you activate the rotor, you get magnetic induction. It starts to spin the anode, okay? So the stator is on the outside. So when the stator fails, the anode doesn't spin anymore. So the electrons bombard one spot. So you can see this is all pitted. So you can see the pitting, and you can see where we have melting of the anode. And this is a stator failure or bearings failure of some sort. So we call it the stator. And we had melting of the anode. So the tube is no longer in use. Okay, the rotor is located inside the stator and inside the envelope. So the stator is on the outside of the envelope, but the rotor is on the inside of the stator. Remember, it's a cup, and it's inside the envelope. So it has a copper cylinder connected to the anode disc by the molybdenum stem. Turns when the stator is energized. The common is 32 to 36 RPMs. High speed is 10,000 to 12,000. Typically in X-ray, we have the common, which is 32 to 36 RPMs. If you go into cath lab or IR, you usually have a 10,000 to 12,000. And you're going to hear the difference between the two. You're going to get a really high-pitched sound with the 10,000, 12,000. All right, so what's making that sound is these ball bearings. They're silver-plated steel ball bearings. They melt a little bit when the magnetic induction happens with turning of the rotor, and they melt a little bit and provide a natural lubricant for those steel bearings with that silver. When the bearings failure, what happens is they start to warp a little bit. As you can imagine, them getting hot and cold constantly with the silver lubricating, this can cause failure. So they wobble sometimes, and what happens is when the X-ray beam hits, it's not hitting the focal track due to the wobbling of the bearings. So, and it decreases your tube efficiency, which is kind of a drag, and it will cause tube failure. You'll start to hear if you start to rotor your X-ray machine, and it's this really high-pitched scream-like sound, those are your bearings, and they're going to go bad. So you can start to hear it get louder and louder and louder, and you know that your X-ray tube is limited in its life expectancy. All right, so your envelope. Easy to see inside when it's the Pyrex. If it's metal, you can't really see inside. So this is a great picture of the Pyrex. They're typically 10 inches long, 6 inches in central diameter, and 2-inch peripheral diameter. Metal is more common nowadays because we ground it so we don't have the tungsten sticking to the inside. It has a window where the photons exit the tube, and it has a vacuum to keep the electrons from interacting with any kind of gases within the air. There's a protective housing around the tube, so it controls leakage and scatter radiation. So when the X-rays come off the anode, it's emitted isotrophically, which means it goes in all directions, okay? So this lead housing is going to absorb a lot of those photons that are going off in every direction. It's made of cast steel, and it's got lead over the cathode side of the tube. And it has a window for the photons to exit. So photons from anywhere else is called leakage. So if it doesn't come off the anode track right here, and it comes off over here, over here, over here, wherever, and it's bouncing off wherever, and it's making it out through the window, then it's called leakage radiation. Okay, so it's leaking out when it shouldn't be there. All right, so this protective housing also isolates high voltage. It cushions the tube from rough handling, and it provides a mean to cool the tube. So we use oil and fans to help cool the tube. All right, control of leakage radiation and scatter radiation. So leakage radiation limit, the maximum amount that's allowed to be outside the lead housing is 100 milliroentgens per hour at 1 meter. So you need to know that. High voltage isolation and tube cooling. So they use dielectric oil. So what that is, it insulates and it protects from high voltage for the radiographer, which is actually really good. You don't want to be electrocuted. It promotes cooling, so it has a gasket on either end to allow expanding and contracting of heat and cooling. The gaskets can blow from vaporization, vaporized tube with oil. So what happens is sometimes when the tube arcs and it can crack the glass or the oil, and the oil can drip onto the really hot anode and cause an explosion. These gaskets will blow out. Very dangerous situation. Thank God it's not common. I've never had an explosion. I've had it to where the oil has dripped on patients and it's really hot. So you obviously need to move that tube away from the patient and get the patient away from it. I've never seen an explosion. I've never heard about an explosion, but I have had oil drip from the housing. So sometimes circulated through a heat exchanger. Now we use that in CT. It's like an air conditioner that it's filtered through to help keep it cool. On our units in X-ray, we have a fan, and you guys can hear the fan in clinic. So we use it to cool the oil because the oil pulls the heat out of the X-ray tube, and then we use a fan to help cool the oil. All right, so off-focus radiation. Now this is a real problem, and there's no way to get around it, okay? So off-focus radiation is photons that do not originate from the focal track or spot. So scattered electrons or photons, the tube housing will absorb most of them. Remember that 100 milliroentgen at 1 meter? So they're going to absorb most of them, but some will exit the windows and cause ghosting. We call it ghosting. I'll show you what that looks like. Contributes up to 25 to 30% of the total primary beam. Huh, that doesn't sound good. So scattered photons from the patient is not capable of creating a diagnostic image of anatomical structures. So that's how you're going to know the difference from scatter and from what off-focus radiation is. It can change a histogram during post-processing in digital imaging as seen as primary beam, and metal tubes help absorb these. So what's happening is it's bouncing off everything inside the tube and then coming out not exactly where it's supposed to be. So the downfall of off-focus radiation is unsharp radiographs, reduction in image contrast, so it's more gray, and increases patient exposure. So this is what's happening here. So you have your electron stream coming across, it's hitting your focal tract, and it's bouncing off everywhere. And it's not, so it's bouncing off the cathode, and it's coming out over here. Okay, so it's not originating from your focal track. Now, what you're going to see here, this is got some off focus within it, but here you can see the nose, the lips, a piece of the mandible right there. That was bone. So this all is off focus. So you can see your collimated beam and you can see your off focus radiation. So that's all bouncing around inside the tube. So the metal tubes help with this, and having your lead housing helps with that. But you still can't get away from your off-focus radiation. All right, rating charts and cooling curves. So there's two rating charts, anode cooling curves and housing cooling curves. All right, tube rating charts. Now, what you need to know is your KVP, your MA, your time, your filament size, and your phase. Also, anything below the line is safe for your heat units. So this is where we're looking and saying, can I make an exposure? So if I have KVP, and say I'm on a 3,400 RPM tube. Here's a 10,000 RPM tube. So both of these are 3,400. Both of these are 10,000. Excuse me. We have 11-degree angle on our tube. We're single phase at 0.6 millimeters. This is a 1.0 millimeter filament. So you got to look and say, okay, what tube do I have? This is a 3,400. This is a 10,000 RPM. Okay, so it's a 3,400. I'm going at single phase, and I have small focal spot versus large focal spot. And then if you have different angle tubes. So normally there's not different angle tubes, but they threw this in there. All right, so then we say, okay, if I have something at 100 kVp, and I need to know, is it safe to make 100 kVp at 75 mass? So here, 175, 100 at 75. So we're looking here. So, I'm sorry, let's do that again. We have 100 kVp and we have 100 MA. Is it safe at 0.1 seconds? Woo! We're right at it, right? So here's the line for 100, and this is 150. So under that is safe. So right at it. If we have, let's look over here at a 10,000 RPM, 3-phase, so large focal spot. If we have 100, and I wanted to use 600 MA at 1 second. 600 MA, I'm above the line. Here's the line right here. Here's 1 second. 600, the line is right there. So I'm above the line, not below. So it is not safe for that machine, okay? So anything below the line is safe. So you just have to figure out what your RPM tube is, what phase it is, generator, and your focal spot size. And then once you find the right graph, then you can look anything below the line. So if I say, we look at this one, if I say at 125, I want a 0.1 second exposure. Am I safe? I can go up to 250, basically. So that's what we're looking at, okay? So nothing too hard, just make sure everything is below the line. But the hardest part is finding what graph you're going to use. All right, so to calculate heat units. A heat unit is calculated by kVp times MA times time, or you can do MAS, and rectification. So a heat unit is a measure of thermal energy applied to the X-ray tube from an exposure. So you have single phase, 3-phase, high frequency. Now high frequency I have seen at 1.45. So don't be thrown. I will give you the numbers I want you to use to calculate. Single phase is always 1. 3-phase does vary, could be 1.3. So just so you know, I'll give you the numbers. This is your factor, okay, your rectification. So your generator type is your rectification. So here, the calculation again, so you need to be able to solve that. Use multiply it, kVp times MA times time times whatever the value is, okay? Easy. So anode cooling charts provides a thermal capacity of the anode and its heat dissipation characteristics. Determines the length of time required for complete cooling following a level of heat input. So how long does it take for the anode to cool? Okay, how long do I need to wait? To use the chart, you have to calculate your heat units first. Okay, so you got to look and see how many heat units are you dealing with. Then you find the total heat units on a vertical scale. So you're going to look at the scale and you're going to say, okay, I'm going to show you what one looks like. You're going to read from the heat units over to the cooling curve and then down to the corresponding time. You're going to calculate the time necessary for the anode to cool to any desired level and subtract the corresponding time from the initial exposure. So here, the maximum that this anode can handle is 350 heat units, 1,000 heat units, okay? And if you were to make the maximum exposure, it will take 15 minutes for the anode to cool back down to zero. So you can make another $350,000 heat unit exposure, okay? So if you're making a 200 heat unit, it's at 2 minutes, okay? So 2 from 15 is 13. So it's going to need 13 minutes to cool before you can make another 200 exposure, okay? So you subtract it from the total amount, whatever heat unit you're going up to, you subtract it from the total amount. We'll practice this in class. All right, so the housing cooling charts, it works the same as the anode cooling charts, so it's the same idea. You're going to look at your heat units, you're going to figure out where you're at. So if you're at 800,000, it's 30 minutes from 150, so 120 minutes for it to cool completely, okay? So that is your lecture on the X-ray tube. If you have any questions, feel free to reach out, send me an email, ask me in class. Either way, it's important that you know and understand what each of these things are, what they do, and how to calculate out your heat units along with finding how long it takes for the tube to cool.